Bismillahirrahmanirrahim. Assalamu alaikum and good evening. Today we are going to discuss the fourth lecture of the topological indices of chemical graphs, and in this lecture we will discuss some computational techniques of distance-based topological indices. In our previous lecture we discussed about some computational techniques of degree-based topological indices, but now we will focus on distance-based topological indices. So here is some of the distance-based topological indices. We will focus on Wiener index, Harary index, and some eccentricity indices. And in our first lecture, we give the definitions of some distance-based topological indices. So let's move to our first task. So let's define the Wiener index. If we have a graph of n vertices v1 v2 up to vn are the vertices of the graph G, then the Wiener index of G is defined as the sum of all the distances between ordered pair of vertices and divided by 2. Remember that we consider here ordered pairs, so that's why we divide with 2. If we consider the unordered pair, then no need to divide with 2. Here we have unordered pair of vertices, so we call it 1. Here we use the ordered pair of vertices, distances between all ordered pair of vertices. Here we use distances between all on unordered pair of vertices. Unordered pair mean distance between A to B and B to A. We will consider ones in our definition, but when we talk about definition 1, in this definition we use ordered pair. That's why the distance from A to B and B to A is count twice. So to normalize the definition, we divide it by 2. So there are two versions of definition. The both have their own importance. Sometimes one is easy to find the Wiener index of some graph. Sometimes the definition 2 is used to find the formula of the Wiener index for some special graphs. So we will discuss this in our next slides. So here we have our first exercise. Find very easy exercise. Find the Wiener index of a complete graph. We know the definition of a complete graph. A graph in which every two vertices have an edge is called a complete graph. So that means when there is an edge between every two vertices, so the distance between every two vertices is 1. So here we will use the definition of version 1 of Wiener index. So this is the formula of complete graph. The Wiener index of complete graph is given as n into n minus 1 divided by 2. So how I try to explain it a little bit. This is very easy. So here we use the definition of ordered pair. Ordered pair mean distance from A to B and distance from B to A, both are counted. So for every vertex V, there are n minus 1 vertices with distance 1. So here are n minus 1. For every vertex V, there are n minus 1 other vertices with whom the vertex V have distance 1. So there are total number of vertices are n. So the formula is quite easily n into n minus 1 divided by 2. So here is are some example for K3. The Wiener index is 3 because you can see that the distance between A to B is 1, B to C is 1, and C to A is 1. So the total distance is 1 plus 1 plus 1 is 3. Similarly for K4, we can see here, this is again a complete graph on 4 vertices. You can see that if we say A, B, C and D, then from A to B is distance 1, B to C, B to D is distance 1, C to D distance 1, A to C distance 1, and here C to B is 1 again and A to D is 1 again. So total sum is 6. And similarly we can find K5 and K6. So this is the general formula for Wiener index of a complete graph. This is quite easily done. So next we have some little bit complicated about I'm saying a little bit complicated, not very much. Find the formula of Wiener index for of a path graph Pn, is representation when n is the number of vertices. Okay, so let's try to explore the formula of the Wiener index for path graph. From the structure of path graph, you can observe that there are n minus 1 pair of vertices at distance 1. So we have n minus 1 pair which are at distance 1. So suppose here in this example we consider n equal to 5. You can see one pair, another pair, and this one, and this one. There are 4 pairs because n is 5, so there are 4 pairs which are at distance 1. So here is n minus 1 pair of vertices are at distance 1, because we have to find the distance between all unordered pairs. So this is ordered pair which are at distance 1. Now we go to the second one for distance 2. Here you can see this is a ordered pair. This is a pair with a distance 2. Here is again a pair of vertices with distance 2, and here another one. So there are 3 pair of vertices which are at distance 1, which is exactly n minus 2. Now move to the in this way we generalize this and find that there are exactly there is exactly 1 pair of vertices which are at distance n minus 1, which are at distance n minus 1. So here we cancel 1 into n. We have only 1 pair of vertices which are at distance n1. So I will summarize again in the path graph. There are n minus 1 pair of vertices which are at distance 1, n minus 2 vertices are which are at distance 2, and similarly we find that there are n minus 1 into n minus 1 pair of vertices at distance 1. So if we have this information, we put this information in the formula of the Wiener index. So here we have a next slide. In our previous slide we observed that there are n minus 1 pair of vertices at distance 1. There are n minus 2 pair of vertices at distance 2. Similar continuing in this way, we notice that there are n minus 3 pair of vertices at distance 3, and similarly n minus 2 pair of vertices, sorry, here are n minus 2 at a distance n minus 2. Similarly here there are n minus into n minus 1 pair of vertices at distance n minus 1. So this is the information we gathered in the previous slide. Here just we put this in the definition of the Wiener index, and we summarize this in a series way. Like here we have you can see that observe that here is 1, here is 1, here is 2, here is 2 again, 3, 3, n minus 2, here is n minus 2, and here is n minus 1, here is n minus 1. So we can summarize this into a series where like I summation I from 1 to n minus 1, I into n minus 1. So we just apply summation on I into n minus 1, and then split the summation and just apply some formulas here, and after some simplification we get the expression for Wiener index for the path graph. So this is the expression n into n square minus 1 divided by 6 for path graph on n vertices. Here is another exercise or another example, Wiener index of the cycle graph. When we talk about the cycle graph, there are 2 cases: when n is even and when n is odd. We will work when n is odd. From the structure of the graph we can observe that if the vertices are odd in number, so we draw a straight line like this and partition the vertex set into left hand side and right. and side. If we observe that the vertex V has distance 1, 2, 3 and 4, again on the right side, if we observe that here is 1, 2, 3 and 4, so here is again 4, here is 4. So in generalized way we can see that the distance of V from one side is 1 plus 2 plus 3 up to so on n minus 1 divided by 2 from one side if we talk about n even, and finally we will multiply it by 2 because on the other side the distances are same. Anyway, we write this in a summation way, like summation 1 I is equal 1 to n minus 1 divided by 2 I. So we use this information in the definition of the Wiener index. So let's see how we use this in the definition of the Wiener index. Like here our graph is C and we use the first version where ordered pair of vertices. You can see that for every vertex, this is 1/2 of formula. There are total n vertices, and as we said, there are two sides and both sides have the same distances, and this is the summation which we gathered in the previous slide. Putting the values of summation, we found that n into n minus 1 divided by 2 into n minus 1 over 2 plus 1 divided by 2, and some simplification we get that the Wiener index of a cycle graph Cn when n is odd is given by n over 8 into n square minus 1. So on the similar lines we can observe that you can find the formula of the Wiener index when n is even. So this is the formula for Wiener index of cycle graph. Another easy example of the Wiener index, which is a complete bipartite graph. So first we define the complete bipartite graph. Let KPQ be a complete bipartite graph where with the set with a vertex subset A with cardinality P and vertex subset B with cardinality Q, and P plus Q equal N, of course the order of the graph. Okay, if you observe the graph, you can see that if we talk about the Wiener index, you can see that if here here is A and here this is the vertex subset B, every vertex of A have distance 1 to every vertex of B. Observe that there are PQ vertices which are at distance 1 because there are P vertices in A and there are Q vertices in B, and both the sets have distance, and both the vertices have distance 1. If you observe that every vertex of A have distance 1 from every vertex of B. So that's why there are PQ vertices which are at distance 1. Now we talk about the same parity. If the vertices V, U and V are in the same set A, then you can observe that the distance between vertices which are in the same set is 2. Similar way, if two vertices are in set B, you can see that the distance between two vertices is 2. So there are P choose 2 and Q choose 2 vertices at distance 2, i.e. vertices of the same set. I mean, when two vertices are in the same set, then the distance between these two vertices will be 2. So we have information 1, there are PQ vertices which are at distance 1, and information 2, there are P choose 2 and Q choose 2 vertices at distance 2. We use this information in the definition of the Wiener index. Suppose Wiener index of KPQ is equal, this is the definition. We have three kind of vertices here, both vertices from the set A, both vertices from the set B, and one vertex from A and the one vertex from B. We observe that when both the vertices are from the same set, the distance is 2, and when we talk about A, the cardinality of A is P, so vertices are P choose 2. Similarly, when we talk about the B, the distance between vertices is 2 and the cardinality of B is Q. So Q choose two vertices here, and when one vertex in A and the one vertex in B, the distance between these vertices will be 1. So there are P into Q vertices which are at distance 1. After some simplification we get that P into P minus 1 plus Q into Q minus 1 plus PQ. So this is the formula to find the Wiener index of the complete bipartite graph. So you can take some example for better understanding here. So now move to some other topological index, which is the Harary index of a complete bipartite graph. This is again an easy exercise. Here we have distance in reciprocal, rest of the things are same. Here set A, set B, one vertex from A, one vertex from B. The only change is that A, the distance is 1 over 2, here the term is 1 over 2, and after some simplification we get the result for Harary index. And this is quite easy exercise. Okay, we move to further some eccentricity based topological indices. The total eccentricity index of generalized complete bipartite KPQ. So first of all we discuss the definition of the total eccentricity index. Summation of all the eccentricities of each vertex in a graph G is the total eccentricity index. So if you observe in the graph, you can see that any vertex in this vertex have farthest vertex at distance 2. Either it is in set A or either in set is B. So we choose again here you can see that because this is complete, so the farthest vertex have always distance 2. So in this way we can say that the eccentricity of each vertex in KPQ is 2. So by putting this information in the formula of the total eccentricity, we found that the total eccentricity index of KPQ is equal to 2 into PQ, where 2 is the eccentricity and there are PQ vertices. So this is the formula for total eccentricity index of complete bipartite graph. Next we move to the next example. The eccentricity index of graph is given as So now we move to the next definition, which is eccentric connectivity index of generalized bipartite graph. The definition of the eccentric connectivity index is given as the summation of the degree multiply the eccentricity of the vertex of all the vertices, the eccentric connectivity index. So we will need to find the formula for the complete bipartite graph for eccentric connectivity index. Observe that the vertices in A has degree Q, vertices in B has degree P, and as we have discussed already that every vertex have eccentricity 2. So observe that the vertices of A has degree Q, the vertices of B has degree P. So the eccentric connectivity index is given as 4 into PQ. This is again a simple formula. In PQ every vertex has eccentricity 2. Further, vertices of set A has degree Q and the vertices of set B has degree P. Putting this information in the eccentric connectivity index, we found the formula of the eccentric connectivity index for complete bipartite graph. So find the formula of the total eccentricity index of a path graph Pn. There are two cases. Okay, so in this exercise we will find the total eccentricity index of the path graph Pn, but there are two cases again depending upon the order of the path graph. We will discuss only one case where n is even. Okay, for n even we have two vertices have eccentricity n minus 1. Of course 1 2 3 4 5, let's we make it 6 here, n equal 6. In this figure you can see that there are two vertices, one vertex and two vertices which have eccentricity 1 2 3 4 and 5. So there are two vertices with eccentricity 5, which is our first one, and again there are two vertices which have eccentricity 4, which is in generalized way, and -2. Continuing in this way, we observe that every eccentricity there are two vertices for eccentricity, every eccentricity, which is 5, 4, and n by 2, and n by 2 mean 3. So this is an easy observation for the eccentricity of every vertex in path graph. So use this information, using this information in our in the definition of the total eccentricity. Total eccentricity of Pn is equal to eccentricity summation of eccentricities of every vertex of a graph G is given as 2, because we take 2 common from every term, and this is the first eccentricity, n minus 1, n minus 2, and continuing in this direction we reach to n over 2. So this is the summation of numbers from n over 2 to n minus 1. So here is the summation of first n terms minus summation of the first n by 2 minus 1 terms. So you can see some this is the sum. After some simplification we get this formula, which is the total eccentricity index of path graph when n is even. Here we use the trick to simplify. Here we use the trick because this is summation is from half to onward. So we take first summation of n vertices, first n integer, first n integer, and minus from first 1 to n over 2 minus 1, which is this is summation of first n terms, and minus summation of first n over 2 minus 1 terms, which is exactly equal to this one. After some simplification we get this formula. Some further more exercises for practice. Investigate the total eccentricity index for Pn when n is odd, because this result is only true for when n is even, and find the formula for eccentric connectivity index for Pn path graph. Okay, so this is all from this lecture, computational techniques from distance based topological indices, but in the last I recommend some exercises for your practice, which is of course good to practice, like investigate the Harary index of path graph, cycle graph, and complete graph. Of course these are some simple examples. What is the formula of total eccentricity and eccentric connectivity index for cycle graph? Derive the Guttman index of here is another degree distance based topological index. Find the formula of Guttman index from Google, and investigate path, complete, CNN, SN. Of course here in Guttman index you will see that the distance is also degree and distance, both are used. Investigate the some distance based. You are open here. This the last question is about open. You are open. Choose any 2, 3, 4, 5 some distance based topological indices, and find these indices for the given graph. Here the graph of this order is n. Here we have, you can see that there are n minus 4 vertices. These are. So please practice these exercises, and when you are good enough to find the distance topological indices for some simple graph, you have a tougher one example open book quiz, like compute the Wiener index of ladder graph. For this you can find many techniques about finding Wiener index and total eccentricity index or other distance based topological index in other ways. So there are more than one techniques to find these distance based topological indices. So you can Google and you can see further literature on this topic. So for this is all from my side about the lecture 4. If you have any question, you can discuss in classroom, or you can comment in the video. Okay, bye.